Well, welcome. It's such a joy to see you all here, and for those who are with us remotely, I'd like to welcome you all to the 2023 Nora and Edward Ryerson Lecture. This year it will be featuring Professor Wendy Freedman, the John and Marion Sullivan University Professor of Astronomy and Astrophysics. This is the 50th anniversary of the establishment of the Ryerson Lectures. They were established in 1973 by the Board of Trustees with the support of a bequest made by the former chairman of the board, Edward L. Ryerson, along with his wife, Nora Ryerson. And as a consequence, this lecture is a truly cherished annual tradition. Actually, for me, I feel like when I consider this lecture, it occupies an extraordinary place in the life, in the pageantry, if you like, of this university and in what it celebrates. It's such a special event. And in the world of science that we'll be hearing about tonight, one of the goals is to have a small set of very fundamental principles, and then to use those principles to try to understand or to organize how we think about the world around us. And in the same way, the university has only a few very fundamental underlying principles, but they matter a lot. And the Ryerson Lecture, and particularly this year's Ryerson Lecture, really bring all of those principles into play in a way that is so important for us. As you know, we are a university founded deeply on academic freedom and freedom of expression. We are a place where we strongly believe that reason, logic, evidence, and rigor should hold sway over authority, dogma, or tradition. And I think we'll see both of those in action tonight when Professor Freedman speaks, where we will see how it is that the struggle for new knowledge plays out, how important these principles are when we seek to understand the world around us. And I think that will be very meaningful. Another foundational principle of the university that matters so much to all of us and that brings us together across the whole university is the sense that all fields of knowledge touch each other, that each one potentially reinforces all the others. And hence it is so important that each year we ask that our community of scholars, our faculty, consider the question of where is there a piece of knowledge that has been created at this university which has now passed the state of being something that's just newly discovered or something that is merely a hypothesis and has passed into a situation where we wish to celebrate it as one of the great products of knowledge that have been created here. One of the examples of the university truly having one of its scholars transform our state of understanding of the world around us. Each time that happens, it's faculty from across the university celebrating the knowledge creation in a particular area, recognizing that that piece is part of the whole edifice of knowledge that we share together. So it's an extraordinarily special moment for us as a university, and it's one that I find deeply moving and that I really enjoy enormously. We're going to be hearing from one of the world's greatest astronomers. She has dedicated her career to understanding the nature of the universe and its expansion by way of fundamental measurement, from its birth and earliest days to its present, and hence also to thinking about its future. Professor Freedman has made truly tremendous contributions to the field of astronomy. She's recipient of the Gruber Cosmology Prize, the Mark Aronson Lectureship and Prize, the McGovern Award for her work on cosmology, and the American Philosophical Society's Magellanic Prize. She has been widely recognized. She's a member of the National Academy of Sciences, the American Philosophical Society, the American Academy of Arts and Sciences, and the American Physical Society, as well as most recently a foreign member of the Royal Society. From her work on the Hubble Constant, she has been acknowledged for her work on the Hubble Constant, the rate at which the universe is expanding over time. She has served as founding chair of the International Consortium to build the world's largest telescope, the giant Magellan Telescope, one which the university, partly because of Professor Freedman, has more than a passing interest. We would surely like to see it built and to see the early measurements that will, of course, change how we can see and understand the universe around it. She has lent her talents towards honing a more refined approach to measuring and understanding our universe so we can unlock an ever greater appreciation of the cosmos. Last year, she addressed the class of 2022 as a commencement speaker, and she told our graduates that in the past century alone, our perspective has shifted from that of a static, fixed universe to one that is dynamic and expanding and now accelerating with time. This change has come about because of new and more accurate data, a growing and evolving understanding of the laws of nature, and the willingness to abandon old ideas. Friedman's distinct willingness to challenge assumptions and chase the best questions as they evolve has allowed her to surface some of the most fruitful ideas in her field. It's also what makes her a true exemplar of the faculty of the University of Chicago. Professor Freedman.
Thank you very much for that very kind introduction. It is a pleasure for me to be here today, and I want to express my thanks to the faculty for nominating me for this honor, and I really consider it a huge honor to be nominated by the faculty. I was talking to Hannah Gray just before we sat down, previous president here, who told me this will be the hardest audience I will ever have, and that it's hard to be nominated by your peers. And I recognize that, so I thank you for that. In a long career, now many decades, there are too many people to list individually who I have worked with, who have contributed to some of the work I will discuss this evening. But I want to say particular thanks to an individual, Dr. Barry Madore, who is my longest standing collaborator and also my husband. And we have collaborated together many times, but I think what we agree on is that the collaboration that we're proudest of is how we raised our son and our daughter. And I'm delighted that my daughter is in the audience with us tonight, and not so happy that our son came down with COVID and wasn't able to be here, but you're probably glad to hear he didn't come. And the joy has extended to another generation, which we're very proud of. And if I go back a generation, I want to express my thanks to my parents. And my mother is also in the audience this evening. And my dad is no longer with us, but he is the person who first inspired me and stimulated my interest in science and astronomy, and I wouldn't be here this evening without him. One of the pleasures of giving this talk is that someone in my family said, gee, I'd like to hear that talk. And pretty soon someone else said, gee, I'd like to hear that talk. So my brother and my sister are also in the audience this evening. And I have other family members here. I won't introduce them all, but that's an unexpected pleasure for me this evening. So thank you for that. And I also would like to thank a number of people in the administration here who in 2014 decided that I really no longer wanted to be in Pasadena and I should come to Chicago, despite the fact that the weather in Pasadena is a little better. And they encouraged me to come. And I also want to thank the administration today, many of whom have really been supportive of this giant Magellan Telescope effort. In fact, took over it. You know who you are. We'll get to you later. And I landed in the Department of Astronomy and Astrophysics which also I'm a member of the Kavli Institute for Cosmological Physics. And I've visited a lot of departments in my career, and I have rarely found one as collegial as this, and not just collegial, but in terms of academic excellence, I really don't think I could have landed in a better place, a better fit for me. Now, the Ryerson is an opportunity to reflect on one's life and one's work, I have heard. So I want to tell you a little bit about my story in a sequence of images of telescopes. And so this is the Canada-France-Hawaii telescope that I'm showing here. It's located at 14,000 feet, Mauna Kea, Hawaii. And the first time, it's on a dormant volcano, and they are very clear to tell you it's not an extinct volcano. And the first time that I ever observed there alone, they handed me the keys to a four-wheel drive truck. I'd never driven a four-wheel drive truck before, and when I got in, I realized that I couldn't both reach the pedals and see over the dashboard. And it was sunset, and so you sleep at a base camp at about 9,000 feet, and then you drive up to the summit to work. And so the sun was coming in directly into my eyes, and I would look down the side and see this precipitous drop, and I think it was one of the most terrifying rides I've ever had in my life. But I made it, and then when I graduated, I went to the Carnegie Observatory, which is located in Pasadena, California. And what I should mention also is the CFHT, at that time, we could actually look, we sat up in a cage called the prime focus cage, and we could look up at the sky above and listen to music through headphones, and it was really exhilarating. Now we sit in warm rooms, we can even observe remotely from home, and then we go to the office the next day, which is not nearly as much fun as going to the mountain. But in any case, in Pasadena, California, I had access to the Palomar 200-inch telescope, which Carnegie ran jointly with Caltech. And then Carnegie owns and operates this site in Las Campanas, Chile. And so the graduate students kindly told me that the mountain would be crawling with scorpions and tarantulas, and I had this image of them all over. And fortunately, they're there, we're observing, they don't bother us, we don't bother them, and it works out pretty well. But the other thing that I was told was that there was a woman behind every tree. I don't know how well you can see, but it's the Atacama Desert, and there are no trees. And it was true then, so I'm happy to report that it has changed, and there are many women who go to the observatory now, but it was an unusual thing when I started. But we had the opportunity with these telescopes on the ground to literally set the groundwork for what became a large project on the Hubble Space Telescope. It was called the Hubble Key Project. And with Hubble, at that time, there was a debate in our community about the nature of the universe, its expansion, its size, and its age. And we didn't know the age of the universe then to better than a factor of 2. People were arguing about whether the universe was 50, well, it was expanding at a rate of 50, which would imply an age of the universe of 20 billion years, or whether it was 10 billion years old, so this factor of 2. So it's as if I meet somebody, how old are you? I'm 25. Well, no, maybe 50, I'm not sure. It's a big difference. And it has a lot of implications for how bright objects are, what their masses are, what the history of the universe is. And so the director of the Hubble Space Telescope, the Science Institute at the time, convened a committee to decide what were the highest priority projects that Hubble could do. And so after finishing my postdoc, I became a faculty member at Carnegie and then ended up being the scientific leader for this project to measure the rate at which the universe is expanding. And then when that project finished, and we resolved the issue. We went from a factor of 2 uncertainty, we measured an uncertainty of 10%. And then I started to work with colleagues at Carnegie to measure very bright objects called supernovae, which also figure into measuring how fast the universe is expanding, as we'll see. And then the directorship at Carnegie came open, and I was selected to become the 10th director of the observatory. And in that capacity, I became the founding chair of the board and leader of this giant Magellan Telescope project. So it's an 80-foot diameter telescope. It's going to be located on a peak at Las Campanas Observatory in Chile. And it's originally, when we started, we had 3 partners. They were Carnegie, Harvard, and the University of Arizona. And under my leadership, we built it into an international consortium that includes Brazil, South Korea, Australia, and institutions across the US, and the University of Chicago is a founding partner. And then in the transition coming here to the University of Chicago, I stepped down as the chair of the board, and Walter Massey, who you've seen in the previous slide, took over. Thank you, Walter, for the 1000th time. And when I came to Chicago, we began a project to improve on our measurements that we've been able to do with Hubble. But what had happened in the intervening time is we made new discoveries having to do with measurements in the background radiation from the Big Bang. And you have people in the audience, people on our faculty here who are experts in that. And as those measurements became more precise, more accurate, it became interesting once again to improve on our measurements of the expansion rate and to test our current understanding of how the universe is evolving. And what I'm really excited about at the current time is now the availability of the James Webb Space Telescope, which was launched at Christmas Day a year ago, that is getting, again, above the Earth's atmosphere like Hubble. It's much more sensitive than Hubble. It's a larger telescope, and I will be able to present some preliminary results here this afternoon that I'm really excited about. So if I look back on my career, I feel very fortunate because when I entered the field, if you applied to the Carnegie Observatories, which I did as a Carnegie Fellow in the 1970s, you got a letter back from the director that said, thank you very much for your application, but we don't accept applications for women. They just didn't take women that recently. And the reason given was because there were no facilities on the mountain for women. Airlines, what's that?
There were no trees.
And there were no trees and no facilities for women. And, so the way this got solved, there was an astronomer named Vera Rubin, and she was so infuriated by this. When she finally got time at Palomar, she cut out a little stick figure with a skirt and pasted it on the door. It said, "Problem solved." And thereafter, so I had the opportunity to do that. I had the opportunity to lead a major project on Hubble after it was launched, to lead a major observatory and a major new telescope facility. So I just feel very privileged and again, really acknowledge the pioneers who came before me that made that possible. Now, before I tell you how we measure the expansion, let me just give you a little bit of the history, and it's interesting because it starts here, University of Chicago. There was a faculty member here by the name of George Ellery Hale, maybe familiar to some of you, and he successively built the world's largest telescope 4 times in a row. Yeah, it was a spectacular career, and including the 60-inch and the 100-inch at Mount Wilson, and those telescopes really changed our understanding of the universe. Edwin Hubble was a graduate student here. We all know his name because of the Hubble Space Telescope. And he came to Mount Wilson Observatory. Hale was the first director, and made some observations. He was interested in objects called nebulae. This is an example. This is the Andromeda Nebula. Now, in those days, the detector that astronomers used was a glass photographic plate. You see here. This is a negative image, so the stars are black here. And these fuzzy objects, many of them had these spiral arms, beautiful spiral arms. And people wondered whether they were regions in our own Milky Way that might be forming new stars, collapsing under gravity to form new stars, or whether they might be what were called island universes, other more remote objects like the Milky Way itself. But there was no way to test how to resolve that debate, and there actually was a large debate over that. And so if you look up at the night sky, so you see stars in 2 dimensions, but you can't tell the 3rd dimension. You don't know the distance to them just by looking. And so what Hubble realizes here, when he's marked this photographic plate, there's a tiny little smudge here between these 2 black lines, and he's written VAR exclamation mark. He's excited about something. And the reason he's excited is he's detected a variable star, VAR, a kind of variable star called a Cepheid, which these stars had been known since the late 1700s, and they have a property that allows you to measure the distance, this 3rd dimension. And what he was able to ascertain was this galaxy now we know as the Andromeda Galaxy. It's the nearest spiral galaxy to our own Milky Way, is not part of the Milky Way. It's located way outside the confines of the Milky Way, and it's a galaxy in its own right. And so Hubble discovered that there were many other galaxies. Here are some beautiful examples of spiral galaxies. We now know there are about 100 billion of such galaxies, different types, in our observable universe. And each one of these galaxies may contain as many as 100 billion stars in 100 billion galaxies. So he enormously increased the size of the universe, changed forever our perspective on the universe that we live in. But he didn't stop there. What he realized is that when he measured the distances to these objects, and he compared them with the velocities, the rate at which these objects are moving, the more distant ones were moving faster than the ones nearby. So velocities had been measured by another astronomer, an investor, Slifo. So you can see here, this is velocity going up, distance to the right, and galaxies that are farther away are moving faster. Galaxies that are closer to us are also moving, but not quite as fast velocities. And together with Albert Einstein, who in 1915 has developed the general theory of relativity, which is a theory about gravity, these observations indicated that our universe, now expanding, it must have been closer at some time in the past. And so as things got closer and closer, denser and denser, hotter and hotter, is what gave rise to our picture now of a Big Bang universe, a universe that started in a dense and hot state and has been expanding ever since. Now, Hubble measured this expansion. I'm just going to give you the number here. He measured a value of 500. And just keep that in mind, because that number has changed over time, not because the universe has changed, but because our measurements have changed, improved. Now, just briefly, how do we measure distances? That was a discovery by Henrietta Swan Leavitt, who was working at the Harvard College Observatory, also measuring the brightness of these stars on photographic plates. And she recognized that the more luminous stars, the brighter stars, were changing in their brightness in a way that was proportional to how bright they were. So the more luminous objects here, these objects can be 10,000 or more times brighter than our own sun, they were taking a longer time to change in their brightness. Now, the atmospheres of these stars are actually in motion. They're moving in and out. And what this relation says is that the rate at which they're changing is proportional to their luminosity. So we wish it was this easy that we just snap a picture and they blink at us, but it takes a lot longer to actually measure the brightnesses of these stars. But this relationship has held over time. It's what we use, what Edwin Hubble used a century ago, and what we use today with the Hubble Space Telescope and James Webb to measure distances. So what it says is if we could go out and measure another period luminosity relation for another galaxy, if those Cepheids are fainter, then because light, we know, decreases in intensity with distance, right? We all know this intuitively. If we see car lights in the distance, they're fainter than those we see if the headlights are right in our faces. And they fall off in intensity as the distance squared, so the inverse square law of distance. So what that says is we measure the luminosities in another galaxy. If they're fainter, we can use that information immediately, directly to determine the distance. So sadly, she got almost no recognition for that, faded into history, but she's now being recognized, I think. We're calling this the Levitt Law after Henrietta Leavitt. So what does the Hubble Constant give us? Well, we can ask some questions just about the nature of the universe. What's its size? What's its age? What's the history of the universe? And these are simple questions, but they're also fairly profound questions that we can ask about the universe, and they all require knowledge of the Hubble Constant, the rate at which the universe is currently expanding. And so just for reference, if the Hubble constant, this value h with a subscript 0, 0 just means we're talking about the current time today, and we're talking about a time 13.7 billion years ago, as we'll see, is the current age that we're measuring, that's the length of time that the universe has been expanding over. So the larger the Hubble constant, the smaller the age of the universe. Now, it turned out to be a lot more difficult to measure this parameter than Edwin Hubble had envisaged. And in the 1960s, here 65 to 1990, here are published values of the Hubble constant. And you can see there's two main groups here, one led by Alan Sandage and Tomon, and the other by Devot Galur. And they were getting very different ages. So here's where the 10 and the 20 billion years came from. There are also other people who were measuring in between, but these were kind of the loudest groups. And yeah. One of who actually tried to get me fired, kicked off telescopes, disinvited from meetings, a number of things. He was, yeah. Anyway, so how did we get past this dilemma? And that really came about as a result of new technology, new techniques, new people, and the ability to now use what we call charge-coupled devices. These are electronic or digital detectors, and replace the photographic plate. So the photographic plate was notoriously inefficient as a detector. So if there was light coming from a Cepheid or another object, say 100 photons were coming toward us from this object, the photographic plate might record one of those, a 1% efficiency. Whereas the CCDs, these solid-state devices, had almost 100% efficiency. And more than that, photographic plates were only sensitive to blue light. So, right, we can disperse light into a spectrum, a rainbow, but photographic plates could only measure the blue light, not red light. And the CCDs could measure blue, visual red, and then we eventually got infrared arrays to go out even farther into the infrared where our eyes can't see. And that's important because there are regions in between where stars are forming that there are dust clouds, and the dust clouds obscure radiation that's coming to us from these distant objects. So for obvious reasons here, this one's called the Horsehead Nebula. I think you can see why. And maybe even better example here, there are stars everywhere except where the dust cloud is blocking the light. So that's a bit of a problem. We're trying to measure these stars, and dust is blocking the light. This is one of the first plots that I made when I was observing with the Canada-France-Hawaii telescope. And we were observing stars, Cepheid variables, with different filters, which we now could do with the CCD detectors. And what I found was that if you made the measurement of this Levitt Law, the period luminosity relation, with a blue filter that only allowed in blue light, the distance that you measured to the galaxy was larger than if you measured it in red light. And obviously the galaxy is at a single distance. And so what it was telling us, and this is a more modern version of this plot where we could observe with the Spitzer satellite in the mid-infrared. But what it was telling us is that when you are observing in the blue, which is shorter wavelength radiation, then if this is your star, here we are as an observer, here's the dust cloud in the way, the blue light is being scattered by the dust or absorbed. And it's not getting to us, or not all of it is getting to us. But the red light, which has longer wavelength, can more easily get through the dust. And so what the CCDs allowed us to say is, okay, well, now we can make measurements at more than one wavelength, which you couldn't do with the photographic plates. And this line here, this curve, is a fit to an interstellar dust law. It had been measured in our own galaxy for stars, bright stars, very well observed. And what it also said is you don't even need to go this far out in the red. You could make even two observations, one in the blue, one in the visual, so these 2 points here, which is what we did with the Hubble Space Telescope, and you could still correct to get the actual distance to the galaxy. But you could make the observations over and over and over on a photographic plate, and you'd still be wrong because of the presence of the dust. And that turned out to be the reason why there had been a discrepancy for long, or one of the reasons. The others were the photographic plates were notoriously inefficient. So when you're measuring the distances to galaxies, my worry has always been if you use one method, like the Cepheids say, you measure it over and over and over, and you could get a very precise measurement because you're averaging over many results, but you aren't hitting the target. And that's a problem. And so if you can use many different methods, and we've been trying to develop many different methods, then you not only can measure something precisely, and this has been called the era of precise cosmology. And boy, I hope we're in an era of accurate cosmology. So this was the philosophy behind the Hubble Key Project. And so the director was worried that if he left it up to a committee to allocate the time, it would be chopped up into tiny little pieces because everybody wanted access to the telescope. We waited decades for this thing to get above the Earth's atmosphere. So he asked a committee to decide what were the important problems that only Hubble could address, and this was the Key Project to measure and resolve this debate about 10 and 20 billion year old universe. So this was our group here. This was my co-PIs here, Rob Kennicott, Jeremy Mould. Here's Barry Madore. And why Hubble? Well, we could get above the Earth's atmosphere. The atmosphere is in motion. It's turbulent. So the light that's coming to us from distant stars is being smeared out, which means we can't make very accurate measurements of the brightnesses of these Cepheids. So the thrust of the program, again, was to measure Cepheid distances, same way Hubble did, but using CCDs, which Hubble had, above the Earth's atmosphere. And so we would start near to the Earth, tie into objects like bright supernovae that we can see to greater distances in the universe, and we were able to overcome this factor of 2. And so plotting in the same way that Hubble originally did, so velocity increasing, distance increasing, but this is the distance out to which Hubble could measure. It all fits within this first tick mark. So we can make measurements now much more distant. And we published in 2001 our final result, which was a Hubble constant of 72, now with 10% uncertainty instead of a factor of 2. And that resulted in an age of the universe of 13.7 billion years. Now, that was sort of short-lived, that we could say all problems in cosmology solved. And very soon after that, it became possible to make more precise measurements of the background radiation from the Big Bang. And so if there had been a Big Bang explosion, you would expect to see some remnants of that explosion. So as the universe has been expanding, it's been cooling, it's now at a temperature about 3 degrees above absolute zero. And you can measure in microwaves the background radiation from the Big Bang. And this is a snapshot of what the universe looked like about 380,000 years after the Big Bang. And the colors here are denoting differences in the temperature, tiny differences. They look very apparent here, but they're only signaling about 1 in 100,000 differences in the temperature across the sky. So that's 0.001%, tiny, tiny little fluctuations. But encoded in those fluctuations, so the temperature is representing differences in the density in the early universe, 380,000 years after the Big Bang. And encoded in these tiny fluctuations is information about the amount of matter in the universe, the rate at which the universe is speeding up in its acceleration, the overall composition of the universe. And these fluctuations are extremely well fit by what we refer to now as the standard model of cosmology. So this is a model that has been around for now almost a quarter of a century. It fits a huge wealth of data, other kinds of data, and is an exquisite fit to the microwave background data. So if you fit that model, it's very prescriptive, and you could then say, what will the expansion rate be today? And the answer that you get is 67. And if the model is correct, then the precision in that measurement is better than 1%. So much better than 10%, which is what we could measure for the Key Project. And so the question is, so anybody see what's in the yellow circle? It's not obvious till you're told. There's an S and an H. Can you see them now? And so cosmologists speculate what that could mean. So what is this standard model of cosmology? And so this model that has been with us now for about a quarter of a century fits an enormous amount of data other than the microwave background, posits that there was this early Big Bang. The universe has been expanding for now 13.7 billion years, and it's speeding up with time. Observations of type 1a supernovae that indicate that, and most of the matter in the universe is dark. And so you had this period, first stars appear, and then you see the first galaxies, and with time, eventually, you come to today, 13.7 billion years, and the Milky Way and other galaxies that we see locally today. And people now are beginning to ask, is this a model that's broken, or are there cracks in this model? Well, what could indicate cracks? the fact that the Hubble constant that we measure nearby is not agreeing with what people are inferring from the microwave background. Sorry, I went back. So here, if we're measuring Cepheids in the nearby universe, we get a value of this Hubble constant of about 72 or 73. And the measurements coming from the early universe, the microwave background radiation, is indicating 67. And so it's as if Michelangelo's painting on the Sistine Chapel and he starts in two different directions and the hands don't meet. That's a problem. And so the question is, what is this telling us? And one possibility is that here we're measuring directly the expansion rate. Here we're measuring, but we have to assume, we have to fit this standard model. Well, maybe something's missing in the standard model. How would we tell? We would compare it with what we measure locally. And there's a group now who are claiming that this difference is something that you call 5 sigma. For the non-scientists in the audience, this is like the gold standard in physics. If an observation has been made at 5 sigma level of detection, you're done. It's really rock solid. And there's a probability, it's been claimed by the people who are talking about this 5 sigma difference, that there's only a 1% probability that this difference isn't real. In other words, there must be something missing from our standard model, and that's the reason why the hands don't line up. So how do we test that? Well, the concern that I've had is that if you only use these Cepheid variables, it's a problem with the rulers. If there's something we don't understand in the Cepheids, then you could be off. How would you tell? You'd want to make measurements in a completely independent way. And that's what we set out to do when I came to the University of Chicago, was to redo the distance scale, avoiding the Cepheids altogether, and do it from the ground up using a different kind of star called a red giant star. Now, this is a luminosity temperature plane. Each one of the points here is representing an individual star. And what happens, we know these stars at this phase of their evolution get brighter with time till they reach a certain luminosity, a certain brightness that is set by nuclear physics, well understood nuclear physics, and they don't get brighter than this tip of the red giant branch, TRGB. You'll notice there are a few stars. It's a different phase of stellar evolution, but many fewer of them. And the stars then become fainter, and we don't see them when we go out now with the Space Telescope and we look in the halos of these galaxies. We can get away from the disk where the Cepheids lie. Cepheids are young. They haven't had time to get away from the regions where they formed. So we have a dust problem in the disk. And we also have the problem there are many stars which could be contaminating the light from the Cepheids. So even though the people at Space Telescope said, you missed your targets, are you sure you want to be pointing out in the middle of nowhere? We assured them, yes, we deliberately put them in the middle of nowhere. But that's actually the outer halos of these galaxies. And when we did that, measured their luminosities, we get a Hubble constant now of 70. So in a 3% uncertainty, which is still larger than what you get from the microwave background. So this is the current state of affairs. So here's the Hubble constant again as a function of year of publication. This is the Key Project value. It was 72 with an uncertainty of 10%. And the uncertainties that come down, you see the sizes of the error bars are decreasing with time. So all the blue are based on Cepheids. The microwave background is black here, and then the most recent observations over the whole sky are here in yellow, the Planck satellite. And here is what is being called the 5 sigma difference between the Cepheids and the cosmic microwave background, and we landed plunk in the middle. We didn't either land right on the Cepheids or the microwave background, but we agree pretty well with the microwave background. So is this a significant 5 sigma result? How are we going to resolve that? And this is how we're going to resolve it. And this is the James Webb Space Telescope, and it's about 3 times the diameter of the Hubble Space Telescope, and it's optimized for the infrared. So there are 18 mirrors that make up this telescope. They're made of beryllium, and they're coated with gold, which reflects the infrared well. And protected, it needs to be a cooled telescope to operate in the infrared. There's a 5-layer sun shield that each layer is about the width of a human hair. But the whole thing is the size of a tennis court. And these 5 layers, they're there to protect the telescope from the sun and the Earth and the moon. And each layer absorbs more and more, reflects more and more until you get to the telescope itself and keeps it very cool. This telescope's now operating about 1 million miles from Earth in a place called the Lagrange point, second Lagrange point. And so you can see the sun shield is protecting it from the sun, Earth, and moon. And it's orbiting behind the Earth around the orbit of the sun. So if you haven't seen any of the images, they're really spectacular. These are some of the early images. You can download them, by the way, from Space Telescope Science Institute webpage and take a look. They're really fun. This one is a deep field. When Hubble first pointed at this field, there were 3 stars that were observable on the Palomar Sky Survey. 4,000 galaxies showed up when they took a really deep image. And then they did a 2-month observation, pointed at the same region of the sky. And this is what you get with James Webb in a 2-hour, not a 2-month integration. So we can only imagine when they get to large surveys later in its lifetime what it's going to look like after 2 months. But there are galaxies here that we couldn't see with Hubble. It showed up in 2 hours. So because James Webb is an infrared telescope, it can see through dust. So here's an HST image, Hubble, of a region. It's called the Eagle Nebula. And it's essentially a stellar nursery where new stars are being born. These are more dense regions and of dust. And this is what James Webb sees. So you can't even really tell from this picture. There's still dust everywhere. It's denser here, but it's all over. And when you look into the infrared, you can see this. So obvious advantage for observing these Cepheids in the infrared. So we got time in the first cycle with JWST, James Webb. It's a 3-in-1 program, so we're looking at Cepheids in the disk. Here's a camera pointed at the outer halo for tip of the red giant branch stars, and a third method that we're checking these two with. Not as well calibrated yet as the other two, but it will be when we're done. And we got time then to do 11 galaxies. Well, this is our first one. This is our group, a small group, 2 students, 2 postdocs. Here's Barry Madore again. And this is our first target. So it's a galaxy at a distance of 60 million light years away from us. So we're seeing it as it was when the light left it 60 million years ago. So that's about 5 million years after the demise of the dinosaurs, so when big mammals were starting to roam the Earth. And that's what the light left at that time. And here's what it looks like with JWST. You can see it's coming into better focus. Now, how do the Cepheids look? So here's a Cepheid in the middle of this red circle. See it? Taken by Hubble. You can see there are even brighter stars in the frame. Here's what it looks like with JWST. And so you can see again, so if you look at these bright images here, the sensitivity in the infrared with Hubble is very low, especially relative to the background. We're going to be able to do considerably better with JWST. And this isn't just one example. They all look like this, all of the Cepheids. They're just hard to see. So for the astronomers in the audience, this is H band at 1.6 microns. With JWST, it's J band 1.2 microns. And our ability to measure the brightnesses of the stars, the sensitivity is much better, the resolution, the clarity of the images. We're clearly going to be able to improve upon the observations. And this is a publication by a group that made these measurements with Hubble. It's a group that calls itself SHOES. So again, here's Henrietta Leavitt's relationship. Brightness is a function of, in this case, logarithm of the period. The scatter is a factor of 2 larger with Hubble than it is now with JWST. So this is just one measurement. These are the Cepheids. We're also doing the red giant branch stars and carbon stars, and we have 11 galaxies to go. So within a year, and we have 4 galaxies this month, which is a little bit like drinking out of a fire hose, but fun. It's delicious. It's really fun. So I think, in the end of this, we should be able to say whether or not we need fundamental new physics, a revision of our standard model, or whether we confirm the current standard model that's been with us for a quarter of a century. And either way, it's important for cosmology to establish. So now let me tell you a little bit about the status of the Giant Magellan Telescope. So here is a video showing here the 7 mirrors that comprise the primary mirror, 6 in a circle, 1 in the center. So this is an 80-foot diameter optical telescope. And up here is a set of smaller secondary mirrors. They have a diameter of 1 meter. So the telescope sits about, it's the size of the Statue of Liberty. We promise not to hurl these mirrors the way they're doing in the video. We'll be a lot more careful. And the telescope mount itself weighs 2,100 metric tons, but it sits on this hydrostatic bearing, so the thin layer of film, so that this thing can move in an almost frictionless way. And here are the secondary mirrors. And so when we're taking an observation, there aren't enough bright stars to actually lock on so that we can keep the camera or the spectrograph fixed. So you have to create stars. We create artificial stars using sodium lasers, and then they reflect back down, and then the 1 meter mirrors, which can be moved much more quickly than the primary mirrors, each one of the 7 of them can correct the primary mirror so that we will end up with a resolution that's 10 times that of the Hubble Space Telescope and 100 times the sensitivity, and correct for the turbulence in the Earth's atmosphere. So just to show you a simulation, this is a star cluster, how it would look on a night on the ground when a telescope in the Andes Mountains, in fact, like Las Campanas. This is a night of good characteristics, what astronomers call seeing. And so you can see these 4 bright objects here. And this is what they would look like with the infrared camera on Hubble. So now we're getting above the atmosphere. And this is what they would look like with NIRCam, the near-infrared camera on JWST. That's what I just showed you, our new observations. And this is what they will look like with the giant Magellan Telescope. And this is from the ground, so we will be able to get these. So just to back up, just to compare, that's the ground, Hubble, JWST, GMT. So you can see why we're kind of excited about this. At this point, we've cast 6 of the mirrors for the telescope. They're being made underneath the football stadium at the University of Arizona. The 7th and final mirror is going to be cast in October of this year. And I'm not going to spend a lot of time now because you probably want cocktails, so I'm just going to go a little faster. We had a blasting of the mountain. This was our Big Bang in 2012. The people who did the explosions here, they colored them red, white, and blue, if you can see that. And that was the color. So the American flag, the Australian flag, the Korean flag, Chilean flag, all have red, white, and blue in them. At that time, that was all the international partners. That was kind of fun. But they wouldn't let us anywhere near it, obviously, but it was loud. The hard rock now has been excavated to make room for the pier for the telescope. So that was completed in 2019. And this telescope's being designed to withstand a 1 in a 500-year level earthquake. So it's in the Andes Mountains in Chile. That's how the Andes Mountains got there, was earthquakes. And that's ready to go. So what we're waiting on now is a partnership with the National Science Foundation. And so here's the timeline. You can see when the mirrors were cast, the site was blasted, excavation. And if the funding can be put into place on a reasonable timescale, then we're looking at what astronomers call first light through the telescope in 2032. So you notice there are actually 8 mirrors here because there is a spare, and that's going to enable us to take out 1 mirror at a time, recoat it with aluminum to make sure that the reflectivity doesn't degrade too much over time. This is an artist's conception of, this is Las Campanas Peak, and this is what the GMT will look like, we hope, in the 2030s. And I'm going to just end by saying it's been a rather remarkable century in astronomy and cosmology in terms of discovery. But when I look ahead to the era that is coming, we're going to have the giant Magellan Telescope. The James Webb now is expected to last 20 years and possibly 30 years in space. There's a new space telescope, the Nancy Grace Roman Telescope, that's due to be launched in 2027. There's the Vera Rubin Observatory, which is being built in Chile, that's expected to be completed at the end of 2024. The LIGO, there's an advanced version of LIGO. It's being upgraded. This is a gravitational wave observatory. Gravitational waves predicted by Albert Einstein. It's opened an entirely new window on the universe. And already on the drawing board are plans for a large ultraviolet optical infrared telescope, another telescope in space, a successor to James Webb and to Hubble. Another remarkable aspect of this is there are University of Chicago people who are now in leadership positions for all of these new facilities. So I think exciting times are ahead, both for astronomy and the University of Chicago. So I'm going to stop here, and I'm happy to answer any questions. Thank you. And we have microphones, right? Yes, there are microphones, so you can. You want to wait for the.
Tail end, you mentioned funding. I'm very curious. Has Congressman Foster from the 10th District, do you talk to him about this? Has it done you any good? Don't mean to embarrass him.
No, in my previous life as chair of the board, I did a lot of talking to people to try and raise funding and raise awareness of the telescope. So Walter Massey, who I saw in the audience a few moments ago, now has that delightful task. And so the answer is we are talking to Congress people. I should also tell you that there's every 10 years in our field, there's a committee of the National Academy of Sciences that's put together to rank proposals for astronomy, both for ground-based facilities and also for space. And this year's decadal survey, so this is an activity that involves about 200 people in our community. And it's a really hard-fought exercise because there are a lot of people and projects, not all of which are ready at any particular time. And this telescope and another telescope project in the Northern Hemisphere were ranked as the #1 priority for ground-based astronomy for the coming decade. So that's a separate step from the National Science Foundation actually having the funds in hand yet to do it, but it's ranked #1, and that is like the Bible in our field. Congress really appreciates that we do our own prioritizing rather than giving them a long laundry list. And so it was not ready for construction in the last decadal survey, but they consider it ready now. So however long it takes for the funding, that's why I'm hoping it will be early 2030s, but we are now dependent on Congress and National Science Foundation to complete the telescope.
He boasts about the fact that he's a physicist and used to work at Fermi.
Yes.
Keep reminding him of that now.
And thank you for the reminder. Yes.
Do any of these telescopes help answer the question of what is dark matter? And why we can't seem to measure, see it, or anything? My understanding is that it's a construct that falls out of the equation.
So the question is about dark matter. I don't know how many people are hearing it in the back, and I didn't have time, or we never would have had dinner, let alone cocktails, to go into what dark matter is. So let me just say a few words about that. So what we have learned in the last few decades is that the matter that we see, luminous matter in stars and in galaxies, turns out to be a small fraction, maybe 1/6 of the total amount of matter in the universe. Then how do we tell that? So I mentioned the Vera Rubin Observatory, and Vera Rubin was an astronomer who was measuring how fast stars are moving in the outer parts of galaxies. And the expectation was, and in fact there was an earlier astronomer at Caltech who found evidence for this dark matter too, even farther back. But if there was no matter, the dark matter, only luminous matter that we see, we would have expected that the speeds at which that stars were moving about galaxies would fall off with distance, in the way that the planets in our solar system decrease their speeds going around the sun as you go out farther from the sun. And instead what happened was these velocities stayed either constant for a long distance out, or in some cases even went up. They weren't falling. And so what that was indicating was that there was somehow matter there that we couldn't see. So that was the sort of first indication. And then people started to make more observations of motions of galaxies in clusters of galaxies. And these galaxies were moving faster than they should have. They would have flown off long ago unless there was more matter there that was holding them there. And then in the 1980s, it became possible to measure X-ray temperature gas, 100 million degree gas, in clusters of galaxies, and it would have evaporated away long ago if there wasn't more matter there. So you get the picture. There's increasing evidence in very different ways that there's more matter there than we can see. And the microwave background observations also are indicating more matter there. So we have not yet been able to determine what this dark matter is. The evidence for it is overwhelming. There's something there we don't see that's causing the luminous matter that we do see in galaxies to behave in a way that it wouldn't otherwise. So there are experiments in underground laboratories that are shielded by lead, that are using silicon and germanium detectors to try and see if this dark matter, in the best candidate now for the dark matter is a particle left over from the Big Bang. So in the 1980s, astronomers were looking for evidence of dark matter, failed stars, dust, all sorts of things that you could think of, and nothing could explain it. And so the best explanation at the moment is that it's a particle that is interacting only weakly. The worst thing would be if it is not even interacting weakly, that it only interacts by gravity. So these underground experiments have been looking for evidence of dark matter. The accelerators, the accelerator at CERN has been looking for evidence as you smash particles together to look for a particle that might explain the dark matter. There's a satellite called Fermi that is measuring gamma radiation, looking maybe for annihilation of these particles. And there's no evidence that we have not found what the dark matter is. So, it's our hope that it will be detected in the next, hope tomorrow. It's a Nobel Prize waiting for somebody, but so far it's remained elusive. In the back.
If that 5 sigma difference holds, what's the leading candidate to explain it?
Well, there are about 1,000 papers on the astrophysical preprint archive that have tried to explain that difference, and none of them so far has come up with a convincing explanation. One of the ones that is still remaining as a possibility is that there was some form, and I didn't talk about dark energy much in this talk either, but something that caused the universe to expand faster early on, but it had to disappear at the time when we can make these microwave background observations, because otherwise it would affect the peaks in the spectrum that are so well fit by these fluctuations in the microwave background. And so there's some hope that there now are experiments of measuring the fluctuations in the microwave background that are sensitive to polarization. So John Karlstrom sitting somewhere in the audience here, I saw him a minute ago. Yeah, hi. And the polarization signal might have a hint if there actually is this early dark energy. We should know pretty soon, right, John? It should really be a very big peak. Now it's a 2 or 3 sigma effect, and if it's real, it's apparently going to be something like 20 or 30 or 40 sigma. So we should know pretty soon. And if it doesn't work, the theorists will have to go back to the drawing board, and eventually, I think, with better observations, and I think James Webb is going to have much better observations, as you've seen from the comparison of Hubble and James Webb. We will resolve this. It is a resolvable problem.
Did I understand correctly that the Magellan is a smaller telescope than the Webb, but it looks like the resolution is going to be better?
No, it's larger. It is 25 meter, and Webb is 6.5 meter. So I use both units, an 80-foot diameter or 25 meter telescope. So it's bigger. So the resolution goes inversely as the diameter. Yeah, bigger telescopes, better resolution. Okay, everybody's ready for cocktails.
It's a huge understatement to say that your work is intriguing and inspiring, and your explanation of it elegant. So thank you very much, Wendy, for a terrific Ryerson lecture tonight. And thank you, everyone, for being here. For those of you who've joined us remotely as well, for everyone in the room, as Wendy mentioned, there are cocktails out in the pre-function space, and we hope you all have a lovely evening. Thank you.